Well, okay, maybe we can start. Thank you for joining us. This is another webinar from the Talent Q program from Quantum Spain project. Today, we have with us one of the best researchers in Spain regarding the quantum computing architecture, that is Carmen Almudever. Thank you for joining us and for delivering this talk. Carmen Almudever is Associate Professor of the Universitat Politécnica de Valencia, where she leads the group of quantum computing architecture. From 2014 to beginning of 2021, she was Assistant Professor of the Quantum and Computing Engineering Department and Group Leader of the Quantum Computing Division at QTech at Delft University of Technology. Her research focuses on different aspects from full-stack quantum computing system, including quantum compilers, quantum error correction, fault-tolerant quantum computation, quantum machine learning, and benchmarking and scalability of quantum computers, especially now in modular quantum computers. Also, she serves as an associate editor of the ACM Transaction on Quantum Computing and Quantum Machine Intelligence journal, and the technical program co-chair of multiple conferences. But most important, she was a co-recipient of several awards that include the 2017 Micro Best Paper Award, 3 High Peak Awards, and the Intel Doctoral Student Honor Program Award. And currently, she is the coordinator of one important project in the AIC Pathfinder Open project that is related on scalable multicore quantum computing architectures. In fact, today she will talk us about scalable quantum computers, transitioning from monolithic, that we have today, to modular multicore architectures. Again, Carmina, thank you for joining us, and the floor is yours.
Yeah.
One additional thing, please, any questions in the chat, or at the end, you can raise your hand to make questions. Sorry, Carmina.
No worries. Thank you very much, Andres, for the very kind introduction, and thank you also, Javier, for having invited me to participate in this Talent Q seminar series. Very good afternoon to everyone. It's a pleasure to be here today. As Andres just mentioned, today I will talk about one of the main challenges of current quantum computer systems, that is namely scalability. As you know, to achieve the full computational power, so the quantum computing promises, current systems that integrate up to tens or hundreds of qubits need to be scaled up and go to processors with the scale of thousands or even millions of qubits. So in today's talk, after reviewing the state of current quantum computers, we will revisit the concept of the full stack. We will focus on different roadmaps in which modular quantum computing architectures are included as a promising path for scaling up quantum systems. We will then discuss about the main challenges that we have in these modular multicore architectures and present some of the work that we are developing within this area. So without further delay, let me please share the screen. So as I just mentioned, today I will talk about the transition from these monolithic current architectures that we have in quantum computers to these scalable modular multicore architectures. So I guess that you will agree with me that the field of quantum computer has made a remarkable progress since the physicist Richard Feynman proposed the idea of building a quantum computer to simulate quantum mechanics back in 1984. So one of the main breakthroughs were, for instance, the development of the first quantum algorithms in the early 90s, or the commercialization of the first quantum computer, or mostly a quantum annealer from the D-Wave company, up to the implementation of the first quantum processors based on different quantum technologies such as superconducting qubits, NV centers, trap ions, quantum dots, you name it. As you know, some of these quantum computers are available to users through the cloud, thanks to the initiatives like the IBM Quantum Experience or the Quantum Inspire here in Europe. So these quantum processors are integrate tens or even hundreds of qubits. Examples of those are the ones based on superconducting qubits, such as the Willow chip from IBM with 105 qubits, or the systems from Rigetti with up to 82 superconducting qubits, or let's say with the processors with the highest qubit count, such as the Condor processor from IBM with more than 1,000 qubits. Also, we look at other technologies such as trapped ions. We have systems integrated up to 56 qubits, or in other technologies such as neutral atoms, we only surpass the 1,000 qubit boundary. That is the case of atom quantum computing. So, thanks to the development of these quantum processors integrating more and more qubits together with the creation of new algorithms, these systems are really integrated what we call the full stack. A full stack is just a series of functional layers that connect the quantum algorithms down to the quantum chip. More precisely, what they provide is high-level languages such as Python to express your algorithm that is compiled into a series of low-level instructions based on Quantum language, and those instructions belong to the so-called quantum instruction set architecture that are further translated into a series of pulses that control and operate our quantum processor. As you may know, for instance, in superconducting qubits, these signals are just microwave signals with a specific envelope, amplitude, and frequency. If we look at the picture of a quantum computer based on solid-state technologies, and we try to map this architecture, so these higher layers that are the software part of our full stack are placed in the classical computer system, whereas these interface layers, more precisely the quantum instruction set architecture and the microwave architecture, belong to the so-called rack where we have the control electronics, whereas the quantum chip is placed, as you know, in the coldest part of this cryostat. Let me talk a bit more about this full stack implementation. So this is what we aim to. Like in classical system, what we would like to have is a series of layers that are well defined, have an R cell contained in which clear functionality is allocated, and they encapsulate the specific information that is only shared between adjacent layers. So again, this is what we aim to, and this is very, very similar to what we have in classical computers, in which this level of abstraction, so this separation between the layers, has been introduced thanks to the abundance of resources. However, in current quantum computing systems, what we have is something more similar to what is shown here on the right. The point is like there is still a tight interplay among the different layers and functionalities, and therefore there is no strict layer structure architecture between them, neither a clear allocation of functionality per layer. As we are increasing the complexity of our system, so as we are increasing the number of qubits, new functionalities need to be added, and therefore they are continually, let's say, moving from layer to layer. On top of that, allowing information going from the lowest level, from the physical level, up to the top layer, and the other way around is not only convenient, but it's a must for being able to extract the most of these still constrained quantum processors that we have nowadays. Therefore, when we design or when we architect these quantum computing systems, it's important to emphasize like three main concepts. The first concept is co-design. That is this thing that I just mentioned about allowing information piercing through the full stack, so top, bottom, and top down, and allowing layers to be informed and when being designed from the other layers of the stack. The second point that I want to make is optimization. So we really want to extract the most of this still constraints quantum processor. Optimization is also a must. And the last one is benchmarking. Benchmarking refers to define a set of quantum applications of algorithms that is representative and in the terms of the workloads that we will have in our real systems, but also, more importantly, a series of metrics that will allow us to measure the performance of our system and also to compare them and even to optimize based on those benchmarks and performance metrics. So say that, coming back to the full stack, as you also know, at the bottom of the stack, at the lowest level, we have the quantum devices. Here we can see what we call the layout of the coupling map for different quantum devices based on superconducting processors from Rigetti, Google Quantum AI, and IBM. What they all have in common is that they still have quite high error rates in terms of operation, still limited coherence time, and limited qubit connectivity. Limited qubit connectivity means that only pairs that are a pair of qubits that are adjacent and sharing this case a resonator can interact. If now we look, instead of looking at superconducting devices, we look at other kind of devices such as trap ions, we see similar or not so similar architectures in which you can have just a linear array of trap atoms, or a more modular architecture that is the one shown here on the right from Quantinuum. In the case in the figure of the left, again we have just a linear array with single trap architecture in which we have a full connectivity between them, so any pair of qubits can interact regardless of the position in this linear array, but there is limited operation parallelization. That's why they came up with this other architecture. This is the so-called QCC architecture that stands for quantum charged coupled device, in which we have several traps of several zones in which qubits or ions can be trapped and operated. In this case, we can enhance the parallelism of the device at the cost of having to shuttle, as we will explain later, the atoms between the different zone traps. But what is common also, common in the previous architectures that I showed, the previous layouts, and also in this one from IonQ, is that they all follow what we call a monolithic architecture, meaning that as we increase the number of qubits just by adding more and more units in the same QPU, in the same quantum chip. So again, this is what we have at the bottom of the stack. At the top of the stack, what we have are the quantum algorithms. Nowadays, we are here in which we still have limited computational power of the devices, but we can still run some interesting algorithms based on a hybrid approach, such as the variational quantum algorithm, on the quantum approximation optimization algorithm, and so on. We are not able to achieve the speed up that promises quantum computers, but it's still good enough. However, we want to be in this other area here, in which with quantum computers we can achieve up to an exponential speed up when we compare with the classical counterparts, but we need a system that is very robust to noise and to errors. So, in order to do so, we need to scale up the quantum hardware, not only in number of qubits, but also in the robustness, such that we can successfully run higher and higher number of gates. And for that, we have to include quantum error correction codes and protocols, improve the design of the quantum algorithms, and therefore close this gap between the system that we have nowadays and the systems that we're going to have in the future. So I guess it's clear from this picture that we need to have a system with higher and higher qubit counts. In order to do so, IBM, as you know, one of the leaders in this field, presented the roadmap back in 2019. And if you look at the bottom part here, one of the main objectives is indeed to increase the number of qubits up to even in the range of thousands or even millions of qubits. Nowadays, we are here today with the Condor processor with more than 1,000 qubits, again, in a monolithic architecture. Of course, as we increase the number of qubits in our systems, we also need to add new functionalities in the top layers, so more in the software layers with, for example, runtime support, or more circuit libraries and quantum write time, or event integration with HPC systems. Now, this goes back in 2019, And a couple of years later, in 2022, so IBM presented an update of their roadmap. And if you look again at the lowest part of the roadmap with where the quantum processors are, one thing or one significant change that you can see is that they go from, again, a single core or monolithic architecture to what we call a modular or multi-core architecture. And of course, again, as we increase the number of qubits, we also increase the functionality that we need on top of that. So again, that was back in May 2022. And just last year, they presented, let's say, a more detailed roadmap that goes in the same direction, in which they split it in a development roadmap. So this is what needs to be developed for going to these scalable systems. So what areas the scientists, researchers, and quantum physicists need to work on. And therefore, this goes together with an innovation roadmap that it's about what we need to include or what we need to add to our systems in terms of software and hardware. As I already mentioned before, in terms of hardware, we need to increase the number of qubits by changing the architecture that we use. And in terms of software, we have to be able to manage this higher complexity with AI, including AI support, or with techniques like circuit cutting and knitting up to the introduction of quantum error correction. So let me go have a closer look at into this part here. So the first thing that they propose in IBM is to start combining QPUs on quantum processors and combine them just with classical links. If they do so, they will not achieve a quantum parallelism, but just classical parallelism between the different processors. This means that if we want to run a quantum algorithm or a quantum circuit that has more number of qubits than there are in a single QPU, you will have to use circuit cutting and knitting techniques to allocate the different parts of your circuit or your algorithm in the different parts of the processor. Again, in this case, you will use circuit cutting and knitting techniques that, as Mar Tejedor explained a couple of weeks ago, they can be gate-based and wire-based. But the problem of these techniques is that the knitting of the construction of the output probabilities increase exponentially with the number of cuts in your device. So that will be one of the main bottlenecks for this cutting and knitting techniques. Now, the next element that they want to include is these connectors or these resonators across chips. They will allow to transfer quantum information, but for example, performing just a swap gate between qubits in the boundaries of both processors, or even creating entanglement between them. On top of that, also look at these other what they call non-local couplers. That those are longer connections within the same QPU. And the reason of these connectors is because one of the goals is also to implement to introduce quantum error correction codes of fault-tolerant protocols into these devices. More precisely, these connectors are required for implementing quantum LDPC codes. LDPC stands for low density parity check codes. So the next step in this modular architecture is to introduce not only classical channels between connecting the different quantum processors and adjacent couplers, point-to-point adjacent couplers, but also quantum links. This will allow not only to have classical parallelization, but also quantum parallelization in your device. In a way, at the end, they will have these systems here combined and connected by classical links and with quantum links. So here you can see that there are different levels of modularities. This will be within a single refrigeration system, but you can also connect different quantum computers or different refrigerators based on optical fibers, and also connect them via entanglement. So the goal of IBM is to build what they call the first quantum-centric supercomputers. As you may know, nowadays we have AI-centric supercomputers, so it will be the same models, but with quantum accelerators. So in these quantum-centric supercomputers, they will incorporate not only quantum processors and quantum networks, but also classical processors together, classical communication networks. And working all together, they will allow to have these systems that unlock the computational power of the current quantum computers. So I guess that it's very clear from this picture the complexity of the systems that we are talking about. Now, as you may know, just last week, IBM published another update or the roadmap, in which, again, as we had before, they split it in the development roadmap and the innovation roadmap. And let me emphasize two things here. The first thing is that they show a more clear path towards quantum error correction. Here, they not only focus in building these modular architectures in which they combine different quantum processors just with classical links and quantum links and at different levels, as I just shown, but they also have a specific proposal for integrating an architecture for integrating quantum error correction based on these quantum DPC codes. So I will go deeper into that, but before, let me also mention that in parallel, they will not also build these modular architectures that include quantum error correction, but also they build these other systems here that it will be used to demonstrate quantum advantage. More precisely, these chips here that they are called, I don't know if I will pronounce it properly, but something like NatWac. They will include in their processors, they will not follow in principle another architecture, but still a monolithic, but and the layout, instead of having a heavy X topology, like in the latest IBM quantum processors, they will go back to a square 2D lattice, meaning that each of the qubits will be able to interact with 4 more neighboring qubits. Here, the idea is to have a 120, by the end of the year, is to have a 120 square lattice in which that will support up to 5,000 gates. And by using this more connected topology, they expect to have an improvement of 16 times better compared to the heavy X chips that they currently have. Now, let me explain a bit more about the changes in these of the details of this roadmap. So as you can hear here in the headlines, so IBM claims that they will build the world's first large-scale and fault-tolerant quantum computer, and they expect that by 2029, so this is 4 years from now, they will deliver what they call the IBM Quantum Starling. That is, again, a large-scale and fault-tolerant quantum computer that will be capable of running up to 100 million quantum gates on 200 logical qubits. So in order to do so, they define 6 criteria that this architecture of this computer should meet. The first one, it's about they should be fault-tolerant. So that means that we have to include quantum error correction, and that we have to achieve logical error rates that are low enough for being able to run meaningful algorithms and applications. The second criteria is that the qubits have to be addressable. This means that individual logical qubits can be not only prepared, but also measured during the computation, not only at the end. Then it has to be universal. That means that we have to be able to define a complete set of fault-tolerant quantum gates that can be applied on logical qubits and between pairs of logical qubits. Also, it has to be adaptive. This is related with the real-time support that we need for decoding the quantum errors and apply the corresponding corrections to those errors. The fifth criteria is that the architecture has to be modular. So this is just what I have shown about these distributed modules that are connected with these quantum and classical links that can be replaced if necessary. And then it has to be efficient, meaning that we have to be able to run meaningful and practical quantum algorithms, and those has to be executed with a reasonable physical resources, and I will add with a reasonable time, of course. So in order to do so, they propose what they call the bicycle architecture that are based on these quantum LDPC codes, and more precisely in specific codes that are called BB codes. So these codes, the good of these codes is that they can offer a higher level of protection, so they can encode more logical qubits using less resources that are required in the surface code. As you know, up to now, surface code is one of the most promising quantum error correction codes, and it still is. But the amount of resources that you need for protecting your information and going to a very low logical error rates is huge. So that's why with these bicycle codes of quantum LDPC codes, we can encode 12 logical qubits just using 144. These are data qubits. We have to also count for Dancela qubits. However, in order to implement that, we will need to increase the connectivity of our topology. Up to now, in surface code, we only need a 2-degree architecture with only near-neighbor interaction, so something like that. But here, to implement this code, we will need to add some extra connections that are long range within the same QPU. So why is that? Because as you can see here in the top picture, this DB code has a toric architecture. So you want to implement this toric architecture in a planar 2D array, you need to connect the boundaries, let's say, with these long range connections between the qubits. So there are other companies that has presented similar roadmaps, although not in so detail like IBM. This is the roadmap, for example, for Google Quantum AI, in which, as you know, they are very focused on quantum error correction, and therefore this is one of those achieving fault tolerance is one of the main objectives. And as you also may know, using the Willow chip last November, they showed that they can go to lower and lower logical error rates if we increase the number of qubits in our logical qubits. Similar roadmaps have been presented by other companies working on trap ion technologies. This is the roadmap for Quantinuum from 2024. Again, here we can only see the kind of architectures or processor topologies that they will have in the following years. Now we are here in this kind of ring architecture. But as you see, as we increase again the number of ion traps in our device, we also have to go to a more scalable design, like a 2D array with different traps in the chip. Also, again, the idea is also to introduce quantum error correction and therefore achieve much lower logical error rates. So similarly to this roadmap from Quantinuum, and continue with trap ion devices, IonQ also has the roadmap in which there is not so much detail, but again, the same idea is to increase the number of qubits and to 2 million of qubits, including quantum error correction, and therefore going to much lower logical error rates. So with this picture, and what I would like to emphasize is that all the companies in different technologies, they are following the several paths, in which one of the major challenges is the scalability, so integrating more and more qubits in our device. To do so and achieving fault tolerance, and to do so, we need to change the architecture of our device and make it much more complex with all this communication that includes classical and quantum communication. And on top of that, we have to include quantum error correction. Now, say that. Turns out that back in 2019, when I was still at TU Delft, and with our colleagues at UPC in Barcelona, we ask ourselves the same question, right? We say, okay, we have these quantum computers. They were much more smaller, at that time. And we ask ourselves, so how is the best way to scale up these quantum systems? And we came up with the same kind of architecture. So at that time, again, back in 2019, and the first papers in 2020, we proposed to use these modular multicore architectures in which several cores are connected via classical links and quantum links. It's not that we're smarter than the others. It's not that we had the idea much earlier. It's just that we apply common sense and we apply the same concepts that we were using in classical computing, right? So since then, we have been working in this topic. And something I think very relevant that we are working on is what we call the double full stack. Remember the stack that I showed before for single core Monolithic architectures? going from application down to the quantum chip. Now, because we are combining these quantum processors and because we are including communications, we are going to this double full stack in which we have a stack on computation that teaches interleaf with a stack for communication. So when we are designing, so these multi-core and modular architectures seem to be very promising, but we need to lay the foundations or to have a mean to really show the potential, of the unique design. So in order to do so, we propose to use what we call design space exploration, which I will not go into the detail, but we perform some analysis in which we take some parameters from the application, from the communication, and from the architecture itself, which we combine and provide as an input for this design space exploration, and output a series of performance metrics or even a figure of merit, which is just a combination of these performance metrics. So we did design what we were able to obtain graph like that, in which we can see how the figure of merit, so how this number, which is just a single metric number that has no meaning, increases. Increases means have better performance as we increase the number of qubits in our system, as expected, but also when these modular architectures or these multiple core architectures can get similar performances as single core, as we also increase the number of qubits and we increase the number of modules. So this is just a way to design and provide some guidelines for the people developing this kind of systems, also to compare them and also to see the potential of each of the proposed multi-core architectures. Now, usually when you have a good idea or you think it's a good idea and you think that it has potential, what you do is to write a project. And this is exactly a project proposal. And this is exactly what we did a couple of years ago. And as Andres mentioned, I have the pleasure to coordinate the Quadrature project, which is an European Pathfinder project. And the goal of this project is to explore the feasibility of architectures that are composed by several quantum chips in order to scale up the quantum system. And this is enabled by a network in package that has a dual character. The first one, it's a network with quantum coherence links that allows the transmission of the exchange of information between the different quantum processors, and a wireless classical network that orchestrates and synchronizes the transfer between the quantum processors, and all of them at cryogenic temperatures. In order to develop and to explore these systems, we do that from this full stack perspective that I was mentioning before. And for that, we have a very nice consortium that includes partners such as Equal One, University of Siegen, and UCD Dublin, who are working on the development of these quantum links. Then we also have partners at TU Delft, at EPFL, working on the transceivers that are required for this wireless communication between the quantum processors. This is classical communication. Then we have University of Catania and Universitat Politècnica de Catalunya working on the communication protocols that are required for synchronizing the different transfers. And at the higher levels, we have the BSc and Universitat Politècnica de Valencia, who work more on the compilation techniques, the applications, and the simulation of these very large systems. Now, say that, let me present some of the works that we have been doing in this project. But before, let me emphasize the challenges that we encounter when we go from this monolithic to multi-core quantum architectures. The first one, it's about the development of these quantum communication links. Again, transferring information from one processor to another is not straightforward, of course. There has been some demonstrations of this transfer in the last years, but there are several options there, and we have to explore which of them is much more promising, depending on the architecture and the technology that we are using. Then the other challenge is the development of these classical communication protocols, the MAC protocols, for instance, for the synchronization again between the different quantum transfers. Then on top of that, we also have to work on compilers, on quantum compilers that are more complex, not only because of the change of the architectures, but also because of the range of the qubits that we have to consider. So when we go to higher and higher complexities, we have to be able to support that and to come up with a quasi-optimal or near optimal solution or have let's say have a good still accuracy when running these compilers, or when compiling the circuits in a limited amount of time. Then another important point, it's about the benchmarks and the metrics that I was mentioning before also for single core architectures. Again, this is a representative set of algorithms that allow us to compare and to design our quantum systems, but also a set of metrics that allow us to compare and to evaluate the performance of them. In this case, those benchmarks and metrics should include not only the computation part, but also the communication part. Also, another challenge is, as I already mentioned, and I think is clear from the IBM roadmap, is the implementation of this quantum error correction codes and fault-tolerant protocols. So the integration of this new layer of complexity in our system, and last but not least, the integration of the quantum computers or quantum accelerators within HPC systems, which is relevant today, but it will become much, much more important once we include this quantum error correction. And other challenges that maybe I didn't mention here. So say that, let me focus on some of these challenges and talk a bit about the work that we have been doing in the last years regarding the development of these quantum computer architectures. So the first thing is regarding the quantum coherent communication links. As I just mentioned, and as you may already know, there are different technologies that are being constructed to allow the interaction between different, or the transferring of information between different quantum processors. There are technologies that are based on cavities. They can be optical or microwave resonant cavities. There is also systems that are based on electro-optical transduction, in which you can translate. Basically, you translate your qubit to a different medium and transport the qubit to a different processor, or you can also use optical channels to perform remote entanglement that is used in large scale quantum networks and the future quantum internet. Here is not only important the technologies that we use, but also the communication method that these technologies would allow us to implement. In other words, there are different ways using these technologies. There are different ways of transferring quantum information. It can be a direct quantum state transfer from one system to the other. It can be a exchange of information based on entanglement. More precisely, we can use quantum state teleportation to teleport the state from one QPU to another QPU, or we can also use disentanglement to perform what we call a remote quantum gate or quantum telegate. So Sahar Benraj, together with Junai Khan, two PhDs in the UPC, they are exploring the feasibility and comparing the different different technologies that they are, the state-of-the-art technologies that we have nowadays, and they do so by performing this kind of analysis in which they sweep some parameters related to the performance of these communication technologies, such as the coupling strength or the cavity decay rate, and they can obtain this kind of maps here. Also, Sahar and Junai, they're also working on the modeling of these quantum communication links. More precisely, they develop a model for a resonant wave mediated cavity that allows, again, the transmission of quantum information from one core to the other. And with this model that is just based on a Hamiltonian and using the Q-tip environment, we are able to see the occupation probability with a lossless system or with a system with higher or lower coupling strength, and also to see how that affects the fidelity of the transferring. So Now, talking about quantum compilers. As you may know, the quantum compilers translate the high-level code into low-level code that is executable in your quantum device. But more importantly, these quantum compilers also perform a series of changes or modifications in your quantum circuit such that it can be adapted to the constraints that we have in our quantum device. More precisely, they do what we call the mapping of quantum circuits, in which they decompose the original circuit to the gates that the gates that are native to the quantum processor. They place the qubits in the circuit into specific physical qubits in our quantum device. Also, they route or move the quantum states to deal with this limited connectivity, and also schedule the quantum operations. And of course, they also perform some optimizations in order to use, for instance, the circuit there. So this process of mapping, again, what it takes is an input, a quantum algorithm, together with the constraints of the quantum processor, and performs a series of steps to adapt the quantum circuit to the requirements of the quantum processor. To illustrate a bit more this process, let me briefly give a specific example. Imagine that you have a circuit that is composed by 6 qubits, and then you have to perform some single qubit gates and some 2 qubit gates. Those are just C nodes that I draw one on top of each other. Here you can see just the Poisson description. So imagine that you want to run this circuit in this quantum processor, in which each of the nodes is a qubit in our system, and each of the edges correspond to the connectivity between the qubits, meaning that, for example, this qubit can interact with those two, but this qubit cannot interact or perform a 2-qubit gate with this other qubit here. So the first thing that this mapping process will do, not necessarily in this order, is to schedule the operations in order to leverage its parallelism. So in order to have like shorter circuit depth and therefore faster execution times, we can parallelize some of the operations in our circuit. The next step will be to what we call the placement of qubits. We can place these qubits here that we have in the circuit randomly in our quantum device. For instance, we can say qubit 0 is initialized here, qubit 1 is initialized here, and so on and so forth. But we can do it in a more optimal way, in a way that we place together those qubits that highly interact. If we do so, for instance, if we see here the first inner gates that are in the first inner gate that is between qubit 3 and qubit 4, this can be performed because these are next to each other. The same for 3 and 5, which they are next to each other, and so on and so forth. However, when we go here, signal between 0 and 5, we see that 0 and 5 don't share a connection. And therefore, in order to make that those qubits to interact, we have to perform what we call the routing of qubits. That is, in this case, the superconducting process is just to add some swaps that exchange the information between them and place the qubits next to each other. In this case, Q and 5 are in neighboring qubits. So the point is, like, I guess that is clear from this example that the process of mapping results in an overhead in terms of operations, because we have to add these extra swaps to deal with the qubit connectivity constraint. So what happens? This example that I show here is just for a single QPU, for a single device. What happens if we go now to these distributed quantum computer architectures? So in this case, the goal of this mapping process will not only to minimize the number of movements within the quantum processor, but more importantly, the main aim will be to minimize the number of intercore communications. That means the exchange between the information between different quantum processors. Why is that? Because these intercore communications are more expensive than the intracore operations, because usually they incur in higher latencies and also in higher error rates. On top of that, they also have to keep track of the qubits in each of the quantum processors, because if you want to transfer to teleport one qubit from one device to the other, you have to make sure that you have a space for that. And on top of that, there are some qubits that are devoted for computation and others for communication. On top of that, this mapping process that I was mentioning before becomes becomes a bit more complex, because you don't only have to map the qubits within the chip, but also for the different quantum processors, again, to minimize these non-local communications. And on top of that, you have to have mechanisms for synchronize the different communications. That means like a global controller or the scheduler of the algorithm. So in this regard, we have been developing different works. Here's the work of a PhD student at UPC, Pau Escoffet, who developed different compilation techniques. The first one that he developed was for this called EPR-based architecture, meaning that we have different cores and we are able to generate this entanglement between them, and therefore to teleport the qubits from one core to the other. Of course, the qubits that will need to interact, that is to perform a two-qubit gate, have to be placed in the same quantum device. To that purpose, he developed the so-called Hungarian qubit assignment algorithm, whatever that means. You can find more details in the paper. And with this algorithm, we can achieve lower number of non-local communications, so non-local transfer between the chips, compared to other state-of-the-art routing algorithms for different quantum circuits. And on top of that, we were also able, to reduce the execution time of the compilation. Remember that as we increase the number of qubits on our system, the complexity of the problem also increases, and therefore we have to be able to achieve still a good accurate enough compilation, but with a specific time for that. Now, he also developed another compilation technique, what a so-called chiplet-based architecture. This is just the first, let's say, the type of modularity that I was showing for IBM, in which we had different quantum processors that are connected with connections among point to point with the qubits that are in the boundaries of the different QPUs. In this case, he developed a rod forcing technique that is based on attraction forces, and with its heuristics, he has some hyperparameters that we can tune and try to find the best configuration of the routing algorithm depending of the quantum circuit that we want to run. In this case, we were able to show an improvement of 3.57 in terms of computation time, also in terms of the ratio of the depth of our quantum circuit, at the expense of being a bit more underperforming in terms of number of intercore communications that were needed. So another example of quantum compiler is not for superconducting technologies, but in this case for trap ions. With our PhD student here at UPB, Annabelle Ovide, we are investigating these modular architectures for trap ions, the so-called QCCD architecture that, as I mentioned before, instead of having a single trap, it is composed by several traps with a specific capacity, and in which qubits needs to be moved from one trap to the other by means of shuttles in order to interact. In this case, he developed the so-called STA algorithm, that stands for spatiotemporal aware qubit allocation algorithm, that the goal is to minimize this number of swaps whenever we run our circuit in this kind of system. In our case, we were able to achieve up to a 50% or 70% of improvement when compared with a random placement of the qubits in the structure or with a greedy state-of-the-art algorithm. Now, last but not least, let me talk about another important aspect that we are looking at. We are also very interested in characterizing, or in other words, in profiling quantum circuits. Why is that? Because usually when we develop compilation techniques or we develop any other, layer of our system, we only look at the restrictions that we have in the quantum processor. However, in order to extract the maximum performance of our quantum devices, we also have to have a look at the characteristics of the algorithm or the circuit that we want to run. To this purpose, we did a profile of quantum circuits in collaboration. This is the work of Medina Bani from TU Delft, in which we derived the main characteristics, not only the usual ones, such as the number of qubits, number of gates, number of percentage to qubit gates, and so on, but we also derived characteristics that are hidden in the structure of the quantum circuit. For that, we use this kind of structures, a qubit interaction graph, which is just interactions of the qubits in the device that can be as complex as this one here, and also the quantum dependency graph, that is just the temporal dependency of the different instructions. And we perform with the using graph theory, we derive the most relevant metrics the most relevant metrics, for the compilation or for the execution of quantum algorithms in multi-core devices. Using these techniques, we can, for instance, see the correlation between the different algorithm metrics with the performance metrics when using different compilation techniques. But more importantly, with these characteristics, we can also synthetically iterate quantum algorithms that mimic the structure of the real ones, and on top of that, control some of the parameters in order to stress some of the parts of the modular architecture. And last but not least, as I already mentioned, another challenge that we have in these modular architectures is the integration of quantum error correction. Here, we will need to go from the algorithm to the selection and the encoding of our quantum information, that is composition of these logical qubits, down to the mapping into the network that is in the different cores, down to the mapping within each of the qubits of each of the cores. Of course, if we want to implement this quantum error correction in modular architectures, that will require, again, a co-design. Examples of co-design is for instance, the 2D array that have been proposed in monolithic architectures for surface code, for instance, or the one that we have seen with these longer couples for quantum LDPC codes, or the other way around. We can think of quantum error correction code that can be run on a specific architecture. So here it's a back and forth process in which we have to see what quantum error correction codes can be implemented or can be implemented in devices, or how these devices are technically feasible for implementing those quantum error correction codes. Another important point is, as I already mentioned, the real-time decoding that will be required to decode or to identify the errors that we have in our system, and in runtime to perform the corresponding correction, and that will require from this classical support. So, but what happens if we don't have, let's say, an architecture or a quantum chip that directly supports the implementation of that quantum error correction code? In that case, also here at UPB, together with the PhD student Laura Rodriguez, she's looking at how compilation techniques affect the performance, or may affect the performance of a specific code when we have limited connectivity in our quantum chip. Here's just an example for the STEAM code. This is just preliminary results, and for different decoder strategies, how the performance degrades once we introduce these extra swaps that are required for dealing again with this limited connectivity. And with that, that's all from my side. But I will not finish this. I will not like to finish this presentation without before acknowledge to all of our collaborators, PIs, PhD students, and postdoc and bachelor students here at UPB, UPC, at U Delft, and at UC. So that's all from my side, and thank you very much. And I will be happy to answer any question that you might have. Thanks.
Thank you very much, Carmina. Very nice talk, and with a lot of topics that is very difficult to select one for asking you. So I hope that our attendees can make questions. You can use the chat, or you can raise your hand in order to ask here any doubt that you can have. Who is the first? Well, as usual. Well, I will start.
Oh, sure.
We have one. Javier.
Hi, Carmen. Thank you very much for the nice talk. So I missed at least some perspective, which I'm sure you can give us, because you're going to run a master that's called photonics and quantum computing. So is there any, crash sentence that you can tell us about how to encompass photonic quantum computing in this framework, the scalability, or?
Okay. Yeah, sorry, I was closing. So yeah, thank you very much, Javier, for the question. So disclaimer. So you're right that we are about to start this master of quantum computing and quantum information and photonics. I'm not expert in photonics. I'm expert in quantum computing, right? So I don't know that much about photonic quantum systems. This is something that we are starting also to explore with another PhD student, Mark Fernandez from UPC. So we are looking now in detail about the scalability of these systems. The same exercise that we are doing with superconducting qubits and trap ions that are a bit more advanced, so at least they have a more clear path towards scalability. We are doing the same for photonic quantum systems. Yeah.
What is what is the main bottleneck in this?
So I will say the way that we compute, right? Because it is measurement-based computer, which is much more different, right? And on top of that, you have a lot of probabilistic processes there. So I guess that, and the number of resources that you will need to achieve, let's say, to have this still logical states, right? So the good thing is there is a way that they are kind of self-protective, like topological qubits. And on top of that, you can use quantum error correction to make the systems even more robust. But still, there are plenty of challenges. So we are now exploring indeed that path on the scalability of photonic quantum computing systems and see how they compare with these other technologies such as ion trap and superconducting qubits that we are more familiar with, right?
Yeah. On top, you can use them at room temperature. So this is big advantage. Nice.
Indeed, that's a big advantage. But still, I mean, you need a lot of, I will say, I don't know what, right? The equipment is completely different, but it's still very, very complex, right? So I'm not sure how that will scale. And on top of that, there is a lot of probabilistic processes there, right?
Well, more questions in this case from my side, because you mentioned direct quantum state transfer. Maybe it's not a common concept because we know teletransport, we know telegate, but what is the direct quantum state transfer?
Then you can couple indeed your qubit, for instance, to your cavity, and the cavity you change the state, you send the state, and the state is received in the other side, right? So that means that you don't need entanglement.
Okay.
So it's the same as transferring the quantum state, but without using entanglement. It's just coupling or transducing your qubit to a different medium or to couple to this resonant cavity. Yeah, that's what I mean by direct state transfer.
Okay. Thank you for the clarification, but I didn't know it. So usually we work at high level, and usually we use teletransport for transporting states between one qubit to another. So you can do exactly the same, but transferring the information through the cavity.
Exactly.
Okay.
Exactly. That's another way to do it. Although you can also use that cavity to change entanglement, right? And still do teleportation or state the gate of tele data, what we are used to. But you can also take the qubit, change it, and send it to the other side, right?
Right. Yeah. Another question that is more related, I work more at the high level, at the software level. So one thing that wonders me is if we will use in the future the quantum circuit concept, like a monolithic program with a lot of instructions, or really we will use something that we have in the classical programming languages, that is subroutines or loops or this kind of structures to program one quantum computer or quantum unit. I prefer to use the word quantum unit, not the quantum computer, because the classical part is unforgettable. You need a classical part always.
Yeah.
So when you're working in quantum compilation and placement and this kind of tools, I wonder if we will have, for example, 1 billion gates, as IBM presented for 2033, a billion. If we will still work in using quantum circuit, or we will work with something more powerful that will mix classical and quantum instructions at the same time.
I think so. I mean, like here, indeed, in the compiler, it can be very complex, and you can use these intermediate representations, right? And for example, in the compiler, in these versions of our, let's say, mapping, which is an algorithm that takes as an input as a circuit. It converts it to a different graph, right? This acyclic graph, and you have instructions, and then you work with that object, right? But indeed, as the complexity of the system increases, maybe we have to change also the structure of that and how we deal with that complexity. Yeah. So I don't know. I don't have an answer to. Might be that we use things that we use in classical computers, as we usually do, right? We use what we know, and we know that works. But it might be something different. But I guess that we will go into that direction. Yeah. But again, the very good question is, so the challenge in terms of the software tools that we use, such as the compiler, is to deal with this higher and higher complexity that we have in number of gates and in number of qubits. Yeah, and still get an accurate solution for that, accurate enough, whatever that means.
Okay.
Yeah. I have another question, Carmina. So what is the status now and the perspectives of improving the intermediate measurements?
Wow,
So
that to be honest, that I don't know.
Okay.
And because this is more a low-level thing, right? We provide, if needed, we provide support for that, Rosy.
Yeah.
That's for the instrumentalists to
give us an instruction about that. Okay.
But I don't know.
Okay.
The only thing is like in the past, when I was still when I was transitioning from QDelf to here, we developed some software support to be able to do this meet measurements and provide feedback support, right? It's like we can provide that's a good question too, because when you know this measurements and then you need some feedback, right? There is some feedback loop that is, let's say, is given closer to the quantum chip, and other feedback that maybe you need to go up to the stack, right? Up to the higher layers of the stack. So depending on functionality, you will have something that is faster or it can be slower, depending on the requirements of that.
Yeah. Okay. Thanks.
Well, the last chance to make a question because we are in the last minute. No? Okay, you know that you will have this presentation in a few days in the TalentQ website. I bet available for everyone. Thank you, Carmina, for this very nice, very interesting presentation. I will see it again because really I learned a lot. And I hope to see you soon in these webinars with new topics that you are working for sure. Thank you very much for all the attendees, and I hope that you will join to our next TalentQ webinar that will be announced soon. Thank you very much. Bye.
Thank you very much. Have a nice afternoon. Bye.